Usually in your machine you'll have a PLC calling the motion program. Usually don't have an operator, standing there typing &1 B1R or something like that. So I'll teach you PLCs first, and then we'll do exercises on both PLCs and motion programs in a group. So a PLC program is different than a motion program in that all of its operations run asynchronously. It's intended for general purpose computation, which could be processing I/O, doing data gathering, checking safety limits. Many times we use PLCs to control the machine, like in a state machine. You can also start and stop motion programs, move motors, do gain scheduling, send updates to your host PC. All sorts of stuff can be done from PLCs. If you want to do any motion from a PLC, you can, but because of its asynchronous nature, the PLC will not wait for the motion command you send to finish before proceeding the program. You need to manually create a construct for that if that's the functionality you desire. You can use the same flow control syntax as in motion programs. So we have the if, while, switch statements. And you can also call subprograms and subroutines through the call, go sub, and go to commands that you'll learn about more in the subprograms section of the training. PLCs are stored in your PLC Programs folder, which is under the PMAC script language master folder in the IDE solution. And the structure for naming your PLC is like this. So you write open PLC and then either the number or the name, just like motion programs. You do not want to mix and match numbers and names. Choose one scheme and one scheme only for all PLCs that you write, either numbers or names. And generally we recommend names because they're more meaningful than numbers. And then you can use the name or the number anywhere when you're issuing PLC-related commands, enabling or disabling or listing, that sort of thing. And those commands are here. So enable PLC and then the name or the number will enable your PLC from anywhere, that is terminal window, motion program, or PLC. Similarly, disable PLC will disable the PLC, and list PLC will list the contents of the PLC to the thread that called that command. You have 32 background script PLC programs that are numbered 0 to 31. Starting from PLC number 0 up to 4 of your PLCs, that is PLCs 0, 1, 2, and 3, can execute in foreground at the real-time interrupt, and you dictate which PLCs can be run in foreground with sys.maxRT_PLC. This is default 0, meaning only PLC 0 will run at foreground rate, but you can increase that up to 3, and then PLCs 0 through 3 will run at real-time interrupt. The other PLCs run in the background cycle. Oh, by the way, you can set the real-time interrupt period with sys.RTInt_period. If you set that equal to 0, then real-time interrupt will run at servo rate. You set it equal to 1, it will run at half servo rate, and so forth. PLCs 4 through 31 always execute in background. Basically, whenever PMAC gets a chance to do background tasks, it will run one PLC, and then the next background cycle it will run the next PLC, and so forth. So first background cycle, PLC 1 will run, next background cycle, PLC 2 will run, and so forth until you reach the last PLC that's enabled, and then it will loop back around. So PLCs will automatically repeat until you disable them, which means that you do not need to encapsulate the contents of your PLC in a giant while loop. It will automatically restart at the top of the PLC every time the PLC has a turn to run. If the PLC was trapped within a while loop, within the contents of the PLC, then the next time the PLC gets an opportunity to run, it will start at the top of that while loop rather than the beginning of the program, and will continue to the end of the while loop before exiting. You can enable and disable multiple PLCs on the same line if you chose numbers. So you can do enable PLC 1.5, 7, 31 to enable PLCs 1 through 5 and 7 and 31. This only really works if you've chosen numbers, not names. Otherwise it gets kind of confusing. And you can see if a PLC is executing by checking PLC bracket and then the name or number dot active. That's equal to 1 if the PLC is running. You can also look in the IDE's task manager. It will show a list of all the PLCs enabled. Oops. So the real-time interrupt PLCs will actually all run every real-time interrupt. So if you have, for example, PLCs 0 through 3 enabled to run in foreground, all of them will run in order every real-time interrupt. Now, something to note about the enable PLC and the disable PLC commands is that you will not necessarily begin or end a PLC at the exact moment you issue enable PLC or disable PLC. Instead, it sets an internal flag that gets checked the next time a PLC has its turn to run. So if within my PLC, I write disable PLC to turn off the current PLC that's executing, it will actually finish doing everything in this iteration of the PLC, and then the next time it gets a chance to run, it will not run. So it won't necessarily stop executing where you issue disable. Excuse me. And I've already said the rest on there. So in PLCs and motion programs, actually, we have standard operators and comparators that you use in programming. So mathematical operators such as arithmetic operations like addition, subtraction, and so forth. But we also have logical operations, bit by bit and or exclusive or and inversion. And you can shift left and shift right using the C-like syntax. We have simple assignment operators, but also more complicated operators like plus equal, minus equal, star equal. Increment and decrement postfix assignments, like plus plus, minus minus, and so forth. If you're familiar with the C programming language, this should be pretty familiar. You also have logical operators and comparators for use in conditions for flow control. Logical or, and, equal to, greater than, less than, greater than, equal to, not equal to, greater than, less than, equal to, and so forth. We have various scalar functions that can come in handy. Trigonometric functions, log exponent functions, rounding, random number generation, all sorts of stuff that we've written actually in assembly, so it's even faster than the standard C library that you'd be using. Right, so here's an example of a simple PLC. All you do is create a counter. We're making a global counter. That way we can put the counter on the watch window. So global counter equals 0. And then open PLC increment. So increment will be the PLC's name. And then inside we put counter plus plus close. So all this PLC will do is every time it gets a chance to run in background, we'll increment that counter by 1. And you can enable it by typing enable PLC increment in the terminal window. So let's, as a quick hands-on, try downloading this and running it from your IDE project. So let's move on to some more advanced ideas. So the flow control syntax is exactly the same for PLCs as it is in motion programs. So we won't rehash that. So you have while loops, if else, and switch. Literally the same syntax as motion programs. Now something we will need to create is a timer subprogram. This is necessary if you want to create a delay in a PLC. In a PLC, you cannot use a delay or dwell command. That's only for motion programs because those are actually considered move commands. And in PLCs, we don't do move commands the same way as in motion programs. So to add a timer subprogram, please go down to your libraries folder, and then there should be, actually this is slightly outdated. We've included a timer template in the more recent versions of the IDE, so let me show you how to get that. In your IDE, go to the libraries folder, and then there should be a file named subprog1 there already. Rename that guy to timer, and then open it. And then inside here, commented out is a timer subprogram. So you want to uncomment the timer subprogram and delete the rest of the junk so that all you have left is the timer section. By the way, a handy keyboard shortcut that might help you with this is Control, what is it? Oops, sorry, not Control. Alt-Shift-Enter will maximize the editor window. That'll give you a little bit more room to see what you're doing. And then to use this in a PLC, you simply use the call syntax, so call timer, parentheses, and then the amount of time you want to wait in the argument. So the call command, you'll learn a little bit more about it when we get to the subprogram section of the class, but for now, just know that's all you need to do. Call timer, parentheses, and the amount of time you want to wait. I think that the new template timer actually has a capital T here, which is different than the slides. So keep in mind that the names you give to your subprograms are case sensitive, so in your case, you want to use a capital T for timer. Okay, so let's talk about a very, very important concept. This concept is not unique to PMAC. It's a programming idea that I really want you guys to pay attention to right here, because if you don't understand this, you can literally hurt somebody accidentally with your machine. So there's level-triggered logic and edge-triggered logic. Level-triggered means as long as a condition is true, continue to execute this block of code, which is fine for simple things like setting variables. Like in this case, say as long as machine input 1 is high, we'll set output 1 to 1. And if it's low, we'll set output 1 to 0. But if you have a motion command in there, it could be very dangerous because you're saying, as long as this is high, continue to reiterate that motion command over and over and over. So if you do something like jog plus 100, jog colon 100 here, then it will continue to move the motor forward as long as this is true, which could be pretty dangerous and may not be what you expect. If that's the case, if you're using like motion in your logic, then you want to use what's called edge-triggered logic instead. So edge-triggered logic says we want to create a separate variable to store the previous condition of your state. And then we look for transitions in state and only act on the transition in state instead of looking at the level of the state. So here we create this global variable called latch1, and then you initialize the latch to store the initial value of input 1. And here we're saying input 1 is just some digital I/O point. Now the latch that you create is generally just going to be an internal variable, and you always want to initialize the latch before you use it in your program. So you can either initialize outside the program if you only plan on running this program one time, or you can initialize inside the program and then encapsulate the whole program in a while loop. And that way, every time you turn on the program, it will first initialize and then run the rest of the program. So that would look something like, instead of having latch 1 equals input 1 outside the program, we would have open PLC edge triggered. And then inside here, we have latch 1 equals input 1. And then you have while 1. And then inside here, we put the rest of the contents of the program. And that way, if you happen to turn off the PLC and then turn it back on, it'll reinitialize the latch. So inside here, I said we want to look for a transition. So we check the value of the input, and then you check the previous value of the input. If they're different, in other words, if the machine input is high now, but it was previous low, then we just saw a transition from low to high. And then we want to act on the transition by doing some stuff. When you act on the transition, you always want to change the value of the latch to be updated to the current state of your condition. So here we're doing some action, and then we're latching the value of the latch to the same value of the input. So input 1 is 1, latch 1 is 1. If input 1 is 0 in the else branch, but it was high, means you've seen a transition from high to low, and you want to do some action and then latch low. So that way PMEC is always aware of transitions in state. Does everybody understand that? It's really important you understand that before you move on, because literally almost every class I teach, people misuse this idea in the exercises. So I just want to make sure you don't do that and save yourself some headache. All right, so if you want to jog from a PLC, you use slightly different syntax than Alex taught you, jogging from a terminal. Jogging from a terminal, you did things like J+, J-, but in a PLC program, you actually write out jog before the command. So you do jog +1, jog -1, jog/1, and so forth. We also have a bunch of other jog commands that are available, besides jogging forward, jogging backward, and closing the loop, which are jog+, jog-, and jog/. You can jog to a specified position with jog equal. So, for example, jog 2 equals 3000 will move motor 2 to 3000. If you want to move to a programmatic position, you encapsulate the position you're jogging to with parentheses. And you can also do a jog equals star, and it will move to the position you've programmed in motor x.prog jog pause. The star just represents that position you've programmed. You can also jog incrementally from present commanded position with the jog : command, incrementally relative to the present actual position with the jog : command. You can return to the pre-jog position with jog ret. And no problem. I need more time anyway.
All right.
Yeah. And you can also jog until trigger by issuing any of the aforementioned jog commands and putting a caret to indicate the trigger move, and then the position you want to move relative to the trigger after experiencing the trigger. So jog equals 10,000, caret -50. We'll try to jog the currently addressed motor to 10,000, but if it encounters a trigger, it will jog backward 50 counts from where it experiences the trigger. But the same jog commands are available to you from the PLC. So to home a motor from a PLC, you actually write out the whole command. So from the terminal window, you are probably doing things like #1 HM, but in a PLC, you actually have to write out HOME. So in this example, we do home 1 to home motor 1 from a PLC. You can also do the home 0 command with home Z. And you can write lists of motors if you want. So in this example, we do home 1, ... 3, 5, ... 7. That home's motor is 1, 2, 3, 5, 6, 7, and skips 4. To kill a motor, that is to remove power from a motor, you use the kill command and then write the motor number after that. So kill 1 will kill motor 1, and you can also do lists of motors in the kill command. And now I mentioned earlier that PLC is by design for asynchronous computations. And if you want to use it to perform motion, you have to create the construct of waiting for the motion to finish by yourself. It does not automatically wait for jog moves or home moves to finish. And the way you do that is by polling the in position bit. So motor x.inPause will be 0 as long as the motor is moving and has not reached its destination yet. So you pull that in a while loop until that becomes 1 and the motor is at its destination. Keep in mind that the in position bit checks to see whether the motor's desired velocity is 0 and checks to see if it's within the in position band. You specify the in position band with motor x.inPause band in units of motor counts, and it needs to stay within that band for the amount of servo cycles equal to motor x.inPause time. So since inPause band is by default 0, it means it's looking for a 0 falling error when desired velocity is 0, which may be a strict requirement if your tuning cannot produce 0 falling error, in which case you would want to expand your inPause band a little bit. You can set it equal to half a count or something like that in case 0 counts is too stringent of a requirement. Now that's for jogging. If you want to wait for a home to finish, you pull not only the inPause bit but also home complete. Motor x.home complete will become 1 when your home has finished. So you want to pull both of these in a while loop before advancing. You can use synchronous variables in PLCs as well, but you need to make sure that you associate the PLC with a coordinate system. It doesn't matter which coordinate system, really, as long as you associate it using the ldata.coord command that I mentioned before. So to associate a PLC with a coordinate system, within the PLC you write ldata.coord equals the coordinate system number, like coordinate system 2, for example. And then you can use synchronous variable assignments in that PLC. In this example, we want to set P1 equal to 1 at the onset of a jog move. Jog 1 equals 100,000. So we use the double equals in assignment for P1. And then P1 will be set equal to 1 exactly as the jog move starts. And then in a while loop, we poll motor 1.inPause until it becomes 1. And once that move has finished, we continue the PLC. So to start motion programs from a PLC, you can use the start n:(m) command. This will start program M in coordinate system n. So in this example, we're issuing start 5:13, which will start program 13 in coordinate system 5. You can also start the same motion program in multiple coordinate systems using the dot syntax or comma syntax. So here start 1.3:5 will start program 5 in coordinate systems 1 through 3. Same thing for aborting a coordinate system. You can use the abort command. For example, abort 10 will stop any motion programs executing in coordinate system 10 and will bring all motors in your coordinate system to a controlled stop. The abort command is different than kill in that it will actually decelerate your motors rather than just cutting power and letting them coast. So it's a lot more safe to use. You can also specify a abort deceleration for each motor. which is different than the deceleration used in the motion program itself. I forget the structure name at the moment, but I can look it up for you later. So here's an example of homing and jogging motor 1 in a PLC. So we've named our PLC jog_home. And within the PLC, we issue home 1 to start homing motor 1. So it'll start looking for a trigger. Now, something very, very important for you to note is I have call timer 0.01 right after home 1. This is really important because PLCs are asynchronous, it will issue home 1 and then move on immediately to the next line. It will move on to this line, and it will start checking whether in pause is 0 and home complete are 0 right away. And it won't necessarily have issued, or it won't necessarily have started the sequencing for the home move before it starts pulling these bits. So if you don't have the call timer, it might say, okay, I'll issue home 1 and then I'm going to check these bits. The PLC is stupid. It doesn't know that you actually want the home to start before you check the bits to see if the home is finished. So you need to force the home command to execute by issuing a small delay before you start pulling these bits. Otherwise, it might say, okay, these bits are actually 1, so I'm going to move on. So once you have finished the home, both of these bits will become 1. The while loop will break out, and then we issue a jog command, jog1 equals 2000. So we want motor 1 to go to 2000. Same thing, we want to issue a small timer delay to make sure the jog has started before pulling the in-pause bit. And then once the in-pause bit becomes 1, we disable the PLC with the disable PLC command, and then the PLC ends. So here's an example of using some switches on your demo box to jog a motor. So here we want to create a latch variable to store the initial state of input 1. And here we're saying input 1 is just the first little toggle switch on the top of your demo box. We'll be using those toggle switches quite a bit in the upcoming exercises. So we're saying if input 1 is on, we want to jog forward, motor 1. If input 1 is off, we want to jog / motor 1. Now, we're using latches so that we only issue the jog command at a state transition. So we're saying if the input 1 is high and it was low, we want to latch the current condition and issue the jog command. Otherwise, if input 1 is low and it was high, then we just saw a transition from high to low, and we went to latch the current condition and issue the j/ or the jog / command to stop the jogging. So that way you can just flip input 1, motor 1 should jog forward, and turn input 1 off, and then it should stop jogging. So this is really similar to a couple of the exercises, so you can use slide 283 as a reference when you're doing the exercises. And these exercises start on page 284. So I'll explain them, and then you'll have all of lunch and then another hour or so after that to do the exercises. So the first exercise, basically it says you want to loop through all of your inputs on your demo box. And the inputs I'm talking about are right here. The top right of your box, you have 8 input switches. 4 of them are toggles, 4 of them are tactile. So if any of those inputs are on, you want to turn on the corresponding output. So if input 1 is on, output 1 should be on. If input 2 is on, output 2 should be on. And if they're off, you should turn output off. I believe I skipped over the pointer mappings for this card, so I'll go over that in just a minute. But you can see on the front of your I/O card, accessory 68E, a series of LEDs. On the left side are inputs. So as you switch your inputs on, you should see LEDs turn on. And the outputs are wired to the output LED array on the top of your box. Now, the outputs won't turn on until you've written your PLC that enables the outputs appropriately. So there's a couple different ways to do exercise 1. You can loop through an array of PTR variables that you've mapped to the inputs, or you can just read the input word and write it to the output word. That'll make sense in just a minute, since I accidentally skipped the section that explained how to map the card, so we'll get to that in a minute. Probably the most efficient way is to just read the input word and write it to the output word. The next exercise is to write a PLC that will jog motor 1 forward while you hold input 1, while you hold one of the tactile switches, which would be input 5, I believe. So you jog plus while you hold one tactile switch, jog minus while you hold a different tactile switch, and stop jogging when you're not holding any of them. The third exercise is to blink a light using a timer. So use the call timer syntax that I taught you earlier. And exercise 4 is pretty hard. It's the longest one. So in this exercise, you want to write a PLC that homes motor 2, waits for the home to finish using the while loop syntax that I taught you. Once it's homed, you want to jog that motor to 5,000 counts, wait for the jog to finish, and then disable the PLC. And please remember, you may need to modify your in-pause band in case your tuning is bad to make sure that the in-pause bit will actually go to 1. If you have any amount of integral in your servo loop, then you can probably use in-pause band equals 0, because the integral would drive the following error to 0, but if you don't have that, you may need to widen the band a little bit. And the solutions to these exercises are immediately after this slide. So if you get stuck, you can look ahead, and there's actually example code that solves all of these exercises for you.